Hello, this is Carsten OZ9 Alpha Alpha Radio with a small video on my dual RF head USB, the calibration and general functioning of the PC software for the dual RF head USB. The dual RF head USB is a device which you can find information on my webpage, moonbounce.dk, and the dual RF head is basically a dual RF input device that can measure from around minus 50 dBm to 0 dBm, and it will tell you in dBm and watts how much power it sees on both of the inputs. Typically, you can use it with the directional coupler, where you measure the forward and reflected power, and it will give you SWR and forward power and reflected power in both dBm and in watt. You can find more information about the device in here, and it's just to give you a quick overview of the device. It has two inputs, RF inputs. It covers from 1 megahertz to 10 gigahertz is the usable range. The range is actually limited to 8 gigahertz, but according to the datasheet for the logarithmic amplifier ADL 5519, it is usable up to 10 gigahertz. And if you calibrate the device in the system where you're going to use it, you can easily use it for 10 gigahertz. Others have used it for that also. It's a small device, and everything is available on the web page. Schematics, Gerber files for PCB and BOM file, and everything is ready or will be made available here once it's completely finished, the project. There's a PC program, a PC tool that will show you the data from the device. There's also you can also get the data out from the device using a normal serial port. The data from the device is a line of data which is repeated about 15 times a second, and it's just a serial ASCII string. But more about that on the web page. You can see how it works. In this video, I will focus a bit on calibration. The dual RF head USB is the same front end as the dual RF head without USB that I originally made. The old or the original dual RF head outputs analog voltages instead of having a USB port. You can look on this page and gain some idea about how that one works. The calibration and so on is pretty much the same for the two dual RF head devices. The principles are the same. The absolute values that you see will be different, but the method is the same. To get started, if you get a dual RF head or dual RF head USB from me, you will get a calibration sheet with the device. The calibration sheet is done at a certain frequency. For this one here, it's done at 3 gigahertz. It is basically a table with power input from minus 40 to plus 5 dBm, and the corresponding voltage that is read from the logarithmic amplifier. I will show you that in a moment how it works. Based on these calculations, the spreadsheet will calculate the slope of the measured voltage. In this case, minus 21.3 millivolts per dB, and it will show you a graph of the measured. You have both the A and B input here, and as they are very close to being the same, they are placed on top of each other, but there are actually two curves here. On the right side of the spreadsheet, there's a couple of calculators. Just a simple one that will convert from milliwatts to dBm. And then there are two sections, A and B, that will calculate the power measured according to the voltage you type in. You can see here that I have typed in these three numbers here is the same numbers as we have over here, the measured calibration values. And the spreadsheet then uses the data, the slope and the intercept points, and based on that and the voltage you type in here, it will calculate the power. And you can see those three numbers here corresponds pretty well with the minus 40, 35, and 30 dBm. The last two here is these two at 0 and plus 5 dBm, and again we are pretty close, 0.9 dB from the measured value. You can also enter, if you have a directional coupler in front with, for example, 30 dB attenuation, you can type in here 30 dB, and it will take the 30 dB into account when it shows you the power and the corresponding the power based on having this attenuation in front of the input. For our case, we'll just enter 0 here. So this is just to give you some background. And again, a low input power yields a high voltage, and a high power input gives you a low voltage. And that goes also for the dual RF head without the USB interface, just to make that clear. The test setup I have prepared looks like this. It is my signal generator SMU200A, currently set at 3 gigahertz and minus 40 dBm. And here you see the dual RF head connected to the output, and the USB connector is going into the PC I'm doing this from. In order to show you how this works, let me find this one here. This is the web interface for the signal generator. So by entering numbers here, I can change the output of the signal generator. I have also started from scratch the PC tool for the dual RF head, and the first thing I will do is I will configure which port it is on, and I know it's on COM21. And selecting so, we see that data is coming into the program. We can go to the details tab, and you can see the info. I explained that in another video, but firmware version of the software running on the dual RF head, the temperature, internal temperature, and the measured forward reflected power in watts and dBm, and also the raw voltage measured on the dual RF head. One thing I will do here, I will put this stay on top so that it will stay in focus no matter which windows are selected. If I bring up this one, you can see right now on the forward port input A, we have 1472, and the calibration set 1471, so that's close enough. This is due to the fact that we are currently putting minus 40 dBm into the device. Now, in order to calibrate the device, we go into to settings here, and we look on the calibration page. This is the default values in a non-calibrated dual RF head USB. And in order to calibrate, we need to put some power into the port, some known power. And in my case, I have connected it, as I said, directly to my signal generator. And I start by telling it that I am inputting minus 40 dBm. and you can see it measures 1472 millivolts. I press the use button. It tells me that it will now take the dBm value, convert it to watts, which will be not much, and it will also read the voltage from the port, and that one will be placed in the voltage minimum forward. Yes, please continue. So you now see that minus 40 dBm was gave us 1472 millivolts. Okay. The next we do is that we go to the signal generator and we enter 0 dBm, and we bring this up. It will not keep focus when I'm doing the setting, so that was why it disappeared. So now I know that I have 0 dBm. That's the max power I'm putting in, and we see we get a reading of 602 millivolts. I just go here, say use, and again, yes please. This is it. Now the forward port is calibrated. I can do a write to device. It warns me it will overwrite. Yeah, okay, and we get out. So now we go back and we click on this. So we now get it in the dBm instead. So what happens up here if I go to this one and I start lowering? You see -3, 4, -5, 6. Let me go down a bit, -10, -15, pretty close, 16, 17, 19, 20. You see we are pretty close. And let's continue down, -28, 29, 30, so on. Let's go to 35. Let's go to -40, 41, 42. And now soon you will start seeing a small non-linearity. You see here we go up, we're about 0.15, and now we are about 0.4 and 0.6 and 1 dB. You see we have about 1 dB difference here. And if we continue and if we get more than 10 dBm below the minimum calibration point, which was -40, it will tell you, sorry, can't calculate because you're outside the calibrated range with more than 10 dB. So let's go up and we can just type in here 0 dBm, and we can go up 2 dB. Now you will soon see a small slight roll off to 0.6 here, 1 dB, 1.4, 1.7. So this is the practical limit is around -50 to 0 dBm. That's where you have the highest accuracy. But you see that it is indeed pretty accurate. Oh, sorry, that was -16. And if we take -25, okay, you see -25. We go into details. We can see the voltage 1140. And I bring up the calibration sheet again for -25, 1139, and we see 3940. So that's how it corresponds. And if we go to let me type in some arbitrary number, -26.8. Okay. -26.8 dBm, that gives us 1178. I go to the spreadsheet and I go here and I say 1178. Okay, it shows me that based on the calibration values and this slope and this intercept point, I should see -26.2 dBm. I typed -26.8, so it's a difference about 0.6, and there's no guarantee that my generator is accurate within 0.1 dB or something like that. So there will be differences. That's why, as I said, it is important to calibrate this inside your system If you, for example, as I showed in the other video, are measuring the power from a power amplifier, a 500 watt PA for maybe 70 centimeters, you will typically use the minimum power, for example, 10 watts, and you will use the maximum power, 500 watts, and use that as calibration factors, and the rest will be very accurate. Now, this was the forward port I calibrated, and in order to calibrate the reference or the reflected port B, I just go to the signal generator and move the output from the signal generator to the B input instead, and then I can do the same for the reflected channel here. It will give me exactly the same results. I could also, to make it a bit easier, let me bring this up again. I could also just take the numbers here that I know that the minimum reflected on the minimum power on the reflected was -40, and I saw 1482. I can type that in, 1482, and I know that the maximum was 0 dBm. Yeah, well, it actually was 5, but I'm using no, just put 5 here, and that was 515 millivolts. 515. That's it. Just write it to the device, and both channels are calibrated. It's that easy. So if I moved the power to or the generator to the B input, you would see the same result as you just saw on the forward power or the forward port. Sorry. And again, click on these, you will get it in watts. Click again, you will get it in dBm. That's pretty much what this video was about. Again, it was just to show you the calibration sheet that follows every device I send out, and how you use that information together with the PC tool. That's it. Thanks for now, and thanks for watching.